Hey guys, welcome to my alkene reaction video series. Today we will be going over hydrohalogenation reactions, which is the addition of hydrogen halides, your chlorine, bromine, iodine, to alkenes to form alkyl halides. Now, I don't include fluorine in this because the bond between the hydrogen and the fluorine is too strong, and fluorine is too much of an electronegative atom to react. So here are some definitions for you to know. An electrophile. It's an atom that is electron poor. It's an electron pair acceptor. That's something important to know, especially when it comes to these kind of reactions, because that's how we're going to be forming these bonds. It also carries a positive charge. Also, another one to know is nucleophile, which is your atom that is electron rich. Now, it always carries either a lone pair or a pi bond. And it doesn't necessarily always carry a negative charge. Just as how you will see here, alkenes are going to be your nucleophile in this reaction. Another important term that I want you to know about is Markovnikov's rule. So that just states that for unsymmetrical alkenes, the hydrogen in the hydrogen halide bond will go to the less substituted carbon, and the halide will go to the more substituted carbon due to stability. And we'll also see that that means that it generates less energy. Alright, carbocations. An ion with a positively charged carbon atom. An achiral molecule just means that it can be superimposed on its mirror image. Alright, so I want you to get down the general idea of the mechanism. Two bonds are being broken. The hydrogen halide and the pi bond in the alkene. And then the next one is two sigma bonds, or two single bonds, replace the pi bond, double bond. The carbon, hydrogen, and the carbon halide bonds are the ones that are replacing these bonds. With all these alkene reactions, there are also exothermic reactions, which just means that the two bonds formed release more energy than the energy needed to break the pi bond. And the most important thing is that they only react with electrophiles. So now let's look at the general mechanism here. So here's your alkene and here's your double bond. Your pi bond is broken. And then here you have your hydrogen halides with hydrogen carrying a partially positive charge and then your halide carrying a partially negative charge. This is due to the dipole moment that is created in this atom. And then as you see, hydrogen is bonded and so is the halide. So the first thing you're going to want to do is locate your carbon-to-carbon double bond. Just know that that double bond is going to want to take the hydrogen away, so you're going to break your hydrogen halide bond. These electrons will go back to bromine, or whichever halide that you have, and you're going to break your pi bond at that point and start forming your sigma bonds. So in this example, the double bond is taking your hydrogen bond, giving the electrons back to bromine, and now you have a cation. Bromine is going to want to bond to that cation and then form your final product. Now, that was a symmetrical alkene. Let's say you see an unsymmetrical one. This is when Markovnikov's rule comes in play. So, as I stated before, the hydrogen halide bond will add to the pi bond to give two constitutional isomers, but only the stable product will be created, which will be the one with the most substituted carbocation. So let's take a look at propene. We're going to add chloric acid to this. So the first intermediate is a first degree carbocation right here at the end. Your second possibility is a second degree carbocation. Which one do you think will form? The answer is going to be the second degree carbocation. Why? Because it has more stability to accept the chlorine atom, and also it has less energy to form. The first degree carbocation will take much more energy due to the instability that it has. So this is the general rule that should apply to all the problems that you encounter with hydrohalogenation. Now, there's one exception to this rule, which is another rule of stability, resonance. So let's say that you have an electronegative atom close to your double bond. Your double bond is going to react with hydrogen bromide and either form one of these two products. Which one is it going to form? Pause this video and see if you can solve this. So the answer is going to be the second one. It's going to form a first degree carbocation. But why? Didn't we just say that Markovnikov's rule states that the more substituted carbocation will form? Well, the issue is that we have an electronegative atom. We have an atom that can be resonance stabilized. So let's draw the resonance structure of this. Let's say the electrons from oxygen want to form a double bond. And it will expel the electrons from your double bond onto the next carbon here, leading way for a positive charge on your oxygen. Oh, let me not forget the methyl group. And a lone pair on your carbon over here. So this is your resonance forms here. Due to this, the first degree carbocation is going to be more stabilized. So let's try out more examples here. Pause the video and see if you can solve both of them. For your first one, your chlorine is going to want to bond to the more substituted carbocation. Your hydrogen will bond to the less substituted one. Oops, sorry. For your second one, chlorine is going to bond to the more substituted one, hydrogen to the least substituted carbon. Alright, so here are some questions to just recap what we learned. Where's the electrophile in the reactions? Let's look back to our last problem. Can you identify which one's the electrophile? If you said hydrogen, you're right. It carries a partially positive charge in the hydrogen halide bond. What about your nucleophile? If you said the alkene, you're right. The alkene is electron rich, therefore it's going to be an electron pair donor. According to Markovnikov's rule, what's the main principle of the Markovnikov's rule? Well, it basically just states that the hydrogen in the hydrogen halide bond is going to bond to the less substituted carbon, leading way for your halide to bond to the more substituted carbon atom for stability. One thing to remember is that wherever you have carbocation intermediates, you can also have carbocation rearrangements occurring. Why does that happen? Well, you want to make sure that you have the most substituted carbocation that you can have. So for example, with this dimethylpentene, it wants to react with hydrogen chloride. Okay, you would think that your secondary carbocation would form because the carbon atoms in the pi bond will only let you do that. So you have to look at the group that's next to it. This dimethyl group. If you were to move this methyl group over, you can actually form a tertiary carbocation. When that happens, it's called making a methyl shift. You can also have hydride shifts, which instead of a methyl group moving over, it's actually just hydrogen, and it'll create the same type of result. So now your chlorine atom will be able to go on to the tertiary carbocation and make way for your most stable product. So far, I've excluded talking about stereochemistry. I wanted that to be like the last thing that we talked about. So just remember, with achiral starting materials, you'll yield achiral or racemic products. Remember that an achiral molecule is one that you can superimpose on its mirror image. With these reactions, stereogenic centers can form. Remember the rule that one stereogenic center equals 2 enantiomers. Let's look at an example. Let's look at methyl cyclohexene reacting with hydrogen bromide. And now it creates a 3-methyl bromocyclohexene. Let's start looking at the stereochemistry of this. One thing to remember is that the hydrogen and the bromine can attack from either side. They can do a front side attack or a back side attack. That doesn't matter. So let's take, for example, this one. What if your hydrogen attacks from the back, and on the adjacent carbon, the bromide attacks from the back as well? Well, now you have a case of syn addition. What if your hydrogen attacks from the back, but on the adjacent carbon, your bromine attacks from the front? Now you have what is called an anti-addition. For syn addition, just remember that both of them are attacking from the same side. Excuse my spelling, I don't know what happened. And on anti-addition, they're attacking from the opposite side. Let's look at another example. Let's say that you're reacting this with hydrogen bromine. Your hydrogen does a front side attack, and then your bromine comes in. You can have 2 enantiomers. You'll either have a syn addition, where hydrogen and bromine both do a front side attack on their carbons, or you can have an anti-addition, where hydrogen did a front side attack and bromine did a back side attack, or vice versa. Just note that a stereogenic center is formed right here, and that you have 2 enantiomers formed here as well. Okay, so now that we went through all of this, let's look at some examples. I gave you guys some tricky problems, so let's go through the first one. Your double bond takes away the hydrogen, and the electrons expel onto bromine, and now you have a tertiary carbocation formed. Now bromine goes in and forms a bond with carbon, and you have a stereogenic center, meaning that you'll have 2 enantiomers form. Both of these enantiomers are trans products, which means that they attack on opposite sides. Now, why didn't I give the hydrogen stereochemistry? Well, the hydrogen's in a methyl group, therefore it won't have a stereochemistry in it. Let's look at the second one. So the double bond attacks the hydrogen, and the electrons expel onto the chlorine, and you have a tertiary carbocation. Chlorine goes in and forms a bond with carbon, and you come out with this product. Why didn't I put in stereochemistry here? Well, this product is symmetrical, and therefore that's why it doesn't have stereochemistry in it. I'll leave you guys with this one final question. If there's stereogenic centers in these problems that we did, Assign an R or S configuration. Leave your answers in the comments below